Welcome back to the online seminar series, Machine Learning Needs Mathematical Optimization. Today we have the pleasure of having José Antonio Lozano, who is currently the Scientific Director at the Basque Center of Applied Mathematics at the north of Spain. And he's also a full professor in computer science and artificial intelligence at the University of the Basque Country. His research interests include machine learning, heuristic optimization, and its application to different scenarios such as biology, medicine, and ecology. José Antonio is a member of the editorial board of many journals, such as IEEE Transactions on Neural Network and Learning System. And he has also been a key figure at major conference, being the General Chair of the IEEE Congress on Evolutionary Computation in 2017. For his ample research output, he has been named a Fellow of the Institute of Electrical and Electronics Engineering, the so-called IEEE, and this nomination was made by the Computational Intelligence Society. So we are very pleased to have you today here, José Antonio, and the floor is yours. And for the audience, José Antonio has agreed to take the questions if you may have them during the presentation. So just put them on the chat and I will read them for José Antonio. Otherwise, you will have the opportunity of asking your questions at the end. Thank you so much.
Okay, thank you very much, Dolores, for your introduction, and thank you very much for inviting me to this seminar series. As you know, it's really weird to give a presentation without people just making a presentation to the screen. But okay, let's try and let's try to make it work. And I hope you can enjoy the presentation. So, okay, let's go ahead. Yeah. So, so the idea of the presentation is to provide you with a tool to analyze data, and mainly to analyze ranking data. To provide you with a tool that you can use to analyze experimental data that you can codify as ranking data. Okay. And my start point will be the null hypothesis testing, and I will make a kind of review of the good and mainly the weak points of null hypothesis statistical testing. This work, or partly this work, has been done together with people at Beckham and people at the University of the Basque Country. I will present it, but all of them have contributed to this work. Okay, so I will start talking about p-values, and I have titled it as "Story of Controversy." We will see why, and then I will talk about a little bit about Bayesian statistics, and I will present a Bayesian alternative for ranking data. Then we will introduce some probabilistic models on permutations, and then we will show some experiments, and we will finish with some conclusions. Okay, so let's go ahead. So statistical methods are all around. Mainly in the last decades, statistical methods have been have had a really high relevance, because many sciences that were scarce of data, now they have a lot of data. We can think in biology. I mean, 30 years ago, biology had almost no data, but now with the new technologies, biology is plenty of data. It's full of data. They have data from sequencing machines, data from microarray data. I mean, they have a lot of data. Similarly, in social sciences, now they can access to many more data than before. And taking into account this amount of data, statistical tests and statistical methods has become as the standard in order to certify scientific truth, mainly in these two fields. I mean, psychology, social sciences, or biology. In order to certify many times scientific facts, you need to carry out a statistical analysis, and particularly a statistical test. However, it came with a problem. Particularly in 2016, Nature, the journal Nature, carried out a study about when there was a reproducibility crisis in science. Okay, because they had some voices that they talk about this reproducibility crisis, so they carry out a survey, and in the survey they discovered that from 1,576 people, they discovered that 52% of them, they assume that yes, there was a significant crisis in science, a significant reproducibility crisis in science. Some of them, 38%, they said yes, a little bit. Some of them, they didn't know. But what were the reasons they argue about this reproducibility crisis? Well, the first reason about this reproducibility crisis is related with selective reporting. Selective reporting refers to only publish those results that are positives. You have a lot of results, and what you do is to put in the paper only those results that really corroborate what you think. Okay. The second cause of this reproducibility crisis is the pressure for publish, something that all we need, all we have probably, and all we know. I mean, we all are researchers, mainly our institutions and our politicians. They put a lot of pressure on us on publishing. But what I'm interested in is in the third cause of this reproducibility crisis. And this third cause was low statistical power and poor analysis. Okay, so here at some point they are implicitly talking about null hypothesis statistical testing, because when they talk about statistical power, they had in mind null hypothesis statistical testing. After this paper that, as can you imagine, it created a lot of polemic in the community. After that, in 2018, the Professors of the National Academy of Science published a paper when they put in question the previous paper. It was titled, "Is Science Really Facing a Reproducibility Crisis? And Do We Need to?" And if you read the paper with some detail, of course, the author, I think is she argues against this reproducibility crisis. But one of the paragraphs says the follows. The occurrence of questionable flawed research and publication practice may be revealed by high rate of false positive and p-hate results. So again, we have here a reference to null hypothesis statistical testing. So it's clear that null hypothesis statistical testing is in the middle of this, let's say, reproducibility crisis, or is in the middle of this issue about the quality and the reliability of science in general. Okay, but the problem with p-values and the problem with null hypothesis statistical testing is previous, because in 2015, several, I think one psychology journal bans the use of p-values. They decide not to publish papers in which they took into account p-values and null hypothesis statistical testing. Again, this created a big problem, because we are all comfortable, let's say, with the use of p-values. Okay, so this is a kind of critique. So and what happened in our fields during that time? In particularly in the field of machine learning, The paper published in 2006 in the Journal of Machine Learning Research by Janez Densar, a statistical comparison of classifier over multiple data sets, was a reference during many years. I mean, probably after the paper, in the next 10 years, if you didn't carry out a statistical analysis of the results using the techniques of the methods provided by Densar, you had a problem to publish the paper. So this paper become a reference for the field. I mean, it was, let's say, from 2006, 2016, something like that. In the field of evolutionary computation, and particularly meta-heuristics, something similar happened with this paper published by Spanish authors. That again, they use. They propose the use of non-parametric statistical tests for comparing heuristic algorithms, and particularly evolutionary algorithms and swarm intelligence algorithms. So there was a lot of controversy about the use of statistical testing, and because of that, for the second time in his life, the American Statistical Association has to write a statement about p-values. Okay, a statement about p-values. I mean, the controversy was so high that they decided to publish a statement about p-values in order to clarify some points about the p-values. Okay, this was in 2016. So basically, they gave some ideas. But before entering the ideas, let's remember what a p-value is. And let me allow to read this, because otherwise I will make a mistake. So a p-value is the probability under a specified statistical model that a statistical summary of the data would be equal to or more extreme than its observed value. Okay? From this sentence, what I would like to emphasize is the fact that a p-value is the probability under a specified and specified statistical model. So the p-value is stick to a specified statistical model. Okay, this is important, and we will see why later. Okay, so the statement basically, or the main statements are the follows. First of all, scientific conclusions should not be based only on whether a p-value passes a specific threshold. Probably we all agree on that, but I'm almost sure that you have seen in a situation in which you have a p-value that is 0.049, and you say, okay, my data has a significant relevance, okay? And at the same time, we probably have faced a situation in which our p-value is 0.051, and we cannot say that there is a statistical significance difference between the data. Of course, it makes no sense, okay? It makes no sense. So this is quite important. I mean, scientific conclusions shouldn't be based only on whether a p-value passes a specific threshold, because we cannot say that this fact is true because I got a 0.049 and is not true because I got a 0.51. Okay, so this is something that is relevant and we should take into account when we carry out a statistical analysis. So another important point is that a p-value or a statistical significance does not measure the size of an effect or the importance of our results. Imagine I have two companies which produce tires, and I would like to know if the size of the tires are different, or I would like to know if they produce the tires with the same size or not. Imagine that there is a really tiny difference between the size of the tires of one of the companies and the other company. if my sample size is 100, probably I wouldn't find a statistical significance difference. But if I have a sample of 10 millions of tires, then I probably would find a statistical significance. So as long as there is a difference, the only thing that I have to do is to increase the size of the sample in order to find a statistical significant difference. So the p-value doesn't say anything about the size of an effect. Okay, it depends on the sample size also. Finally, and that something that is also important is that by itself, a p-value does not provide a good measure of evidence regarding a model of a hypothesis. The fact that I have a p-value of 0.5 doesn't say anything about the null hypothesis. It doesn't say that the null hypothesis is true, because there could be many different hypotheses that can match the data. Okay, so a p-value does not provide any evidence about a model or a hypothesis. Okay, so with all these statements, at the end they make some recommendations. The American Statistical Association, in this statement, they made some recommendations, and one of these recommendations is they propose some alternatives, and one of these alternatives is Bayesian methods. Okay, so the idea is that in order to analyze data, we should have as more information as possible. Okay, and one way to provide more information than just a p-value is to use Bayesian methods. So the idea of the talk is to provide you with some methodology to use Bayesian methods in one specific case in which I have data from some experiments. Okay, so this is the main idea. Yeah. So I don't know how familiar are you with Bayesian statistics. So because of that, I'm gonna give you 3 slides introduction to Bayesian statistics that is really difficult to summarize Bayesian statistics with 3 slides. Because Bayesian statistics is a different way of thinking in probability and a different way of thinking on how probability is used. Okay, so I'm not gonna enter in philosophical questions because there are many philosophical questions associated with Bayesian statistics and with frequentist statistics, but I'm gonna give you an idea of what is the main the main idea of the machinery of Bayesian statistics. Okay, so in order to introduce Bayesian statistics, I'm gonna give you an example. Let's consider a coin. Let's consider that we have a coin, and we have a sample of flipping the coin n times, and I would like to calculate the probability of the next flip of the coin. Okay, I would like to compute the probability of the next flip of the coin, given that I know the sample size. I know the sample size, no, I know the sample. I know x1 and xn. I mean, this will be tails of heads. Okay, this will be tail of heads, and I would like to know what is the probability of tail in the n+1 time, or the probability of heads in the n+1 time of flipping the coin. Okay, so a frequentist approach, what we would do in a frequentist approach is to carry out an estimation, for instance, of the probability of heads using the sample. Okay, usually we try that this estimator has low variance and low bias, and then we use this estimator to compute the probability of heads and the probability of tails in the next flipping of the coin. Okay, this is the classical frequentist approach. In the Bayesian approach, what we assume, and this is really weird the first time you heard that, is that we assume that theta is a random variable. Okay, so now theta is not a parameter, but a random variable. And this random variable codifies the distribution of this random variable, codifies the uncertainty we have about the parameter. Okay, so imagine that I know that this company is producing coins that are not completely balanced. Okay, so I could use that information and introduce in the probability, in the what is called the a priori distribution over the parameter theta. Okay, so instead of assuming that theta is a parameter, we assume that theta is a random variable. So once we are given some data, using the Bayes theorem, what we compute is the probability, what is called the a posteriori distribution of the parameter. Remember that theta is a random variable, so I can compute the probability a posteriori is the parameter given d. If you realize about this formula, I think you can see my hand here. So you have here the a priori distribution. This is the log likelihood, and this is the probability of d. So if I compute the probability distribution, the a posteriori probability distribution, and I can finally compute the probability of heads and tail given d as a this formula. Okay, as a this formula, the one on the bottom.
José Antonio, we are still in a previous slide, we believe.
Oh my God.
I'm seeing a little bit of Bayesian statistics. That's what I'm seeing, the slide.
Oh
so
my
maybe...
God, you are here in 2. I don't know what is going on. Okay. Let me...
maybe you can share your screen instead of the...
Yeah, I think I'm sharing the screen. I'm not sharing the...
I'm
sharing the screen, no the file. Okay. So should I start from a little bit of Bayesian statistics or continue?
That's what we were, yeah, this is where we were.
Now, okay. So now you are in the outline, okay?
Yes, we are.
Okay, and now you are in the Bayesian statistics example?
Yes, we are.
Okay. So do you want me to continue from here, or should I go ahead?
I think we understood what you meant. I just wanted to make sure that...
Okay, that we are in the process. Okay. So we were here. Okay. I don't know if you can see the mouse. Can you see the mouse?
Yeah, we can. Yes, we can.
Okay. So now we are in the slides when I put the Bayesian approach. Yeah, it's okay?
Yes, it is.
Okay, so let's go ahead. If there is any problem, just tell me. So this is the Bayesian approach. Okay, as you see, it's a little bit different than the frequentist approach because you suppose that the parameters are random variables that from someone that has been using frequentist probability, has been using usually probability, it's a little bit weird, but I mean, as long as you use it, you more or less you understand. So if you check with detail this formula, basically what you do is to compute the probability of heads, for instance, given theta times the probability of theta given d. So we are computing more or less the expected value of xn plus 1 given the distribution of theta. Okay, of course. The Bayesian approach has its own problems. For instance, the first problem is how to choose p theta, how to choose a proper a priori distribution. The idea of the a priori distribution is that it contains the information that you have about the event you are trying to model. Okay? So, for instance, if you want to predict if, I don't know, Real Madrid is gonna win, I don't know, to Athletic de Bilbao, probably you can assume that the probability, a priori probability that Real Madrid beats Athletic de Bilbao is higher than 0.5. So you can put that information in the a priori. Okay. So another problem is how to compute the a posteriori distribution, because this is not easy. And it's not easy computationally. Sometimes there is a closed formula, but many times you need to sample this probability in order to compute. And this the same for this formula. Okay, sometimes there is a closed formula for the probability of xn plus 1 given d, but sometimes there are not. And then, well, you have to manage to compute it. Most of the time, Markov chain Monte Carlo methods or Gibbs sampling are used. Okay, and we'll see in fact, we will see that we will in our environment, we will have to use that kind of methods. Okay, so let's see an example. Let's continue with the example with the flipping a coin example. For instance, in the flipping a coin example, we could assume that our a priori distribution over the parameter, that is just the probability of heads or the probability of tails, is a beta distribution with parameters alpha h and alpha t. These alpha h and alpha t are usually called hyperparameters to distinguish from the parameter of the distribution. Okay, you can see that the beta distribution is quite flexible. So for instance, if we use a beta 1,1, we do not make any assumption about the parameters. So we assume that all the parameters have a priori the same probability. If we use a beta t22, we can assume that, well, the highest probabilities in 0.5 and so on. As you can see, there are many possibilities. So choosing different hyperparameters, you can have different distributions. Okay.
Antonio, could it be that the slides are not moving again?
Again, I don't know what is going on. Okay, now are you going back?
I have not seen much move. Yeah, so.
I don't know what is going on. Okay, I don't know if we can try. Okay. No. Okay, one thing. Okay, let me try to show the screen this way. Let's see if this way. Okay, let me. Wait a minute. I'm gonna do a different thing.
We can see it in that way. It's not. Yeah, it's not a problem.
Okay. Let me. And what I'm gonna do is to put here the slides. Okay. Let me see if I can put the slides here, but I don't want to. Okay. Now you can see this slide. Okay. So in the case of the beta distribution, what it happened is that if I have the sample, and in the sample I have h number of heads and t number of tails, the probability, the a posteriori probability is again a beta distribution where the new hyperparameters are alpha h plus h and alpha t plus t. So I mean, it works very well because I have a closed formula for the posteriori distribution. And in this case, we also have that the final probability can be computed in this closed form. Okay. In this case, it says that the beta distribution conjugate with the Bernoulli distribution. Okay, because if I have a priori a beta distribution, after I see the sample, I continue having a beta distribution. Okay. Unfortunately, this won't be the case usually. We will have. Okay, we don't be so lucky most of the times. Okay, so that's the idea more or less of this is a really rough idea of what Bayesian statistic is. Okay, and now we go to our data. Okay, to our approach. So what we want to do is to analyze some kind of data that is the output of some experiment of applying, for instance, an optimization algorithm to some problem instances, or some classifiers to some classification problems. Okay, I'm going to illustrate this with optimization algorithms, but it could be illustrated with classifiers, for instance. Okay, so basically, what I do is I have some instances of the traveling salesman problem. I hope that you all know traveling salesman problem. I have some instances of the traveling salesman problem. I have some heuristic algorithms, a genetic algorithm, some particle swarm optimization, estimation distribution algorithms, a local search, differential evolution. I apply the algorithms and I obtain some results. Okay, because it's the traveling salesman problem, the lower the better. And these these results are paired because I can compare the GA and the EDA in the TSP in each of the instances, but are not comparable in the sense that I cannot compare the result of the GA in the first instances of the traveling salesman with the result of an EDA in the second TSP. So I have to compare this way by columns. So for each column, for instance, what I can do is to obtain a ranking of the algorithms. So if I try to obtain a ranking, what I see is that the EDA is the best algorithm, the second best is the PSO, third best is GA, fourth best is local search, and the worst algorithm is differential. So I can do the same with the rest of algorithms, and then I have this situation, and then my output of the experiment at the end is gonna be a set of rankings of matrices.
José Antonio, are you on slide section 3?
Yeah, I am in the problem and the data set. We are not I don't know what is going on. Okay, can I, maybe I'm gonna try a different program and see if it works. It's the collaborative. Okay, now I am in okay, let me, I think I can see the slides here. Oh, no. Okay, let me try with okay, let's try with a different program to see if it works, okay? I'm in the 33 now.
So I think if perhaps we can share your PDF. You have a PDF there, right? So maybe we can share that.
Okay, I'm gonna try. So let me.
Yeah.
Let me try. So I'm gonna stop. I stop sharing the screen. I'm gonna share the file. Okay. Okay, I'm gonna add the file. So wait a minute. Okay. Why? Okay. It goes really slow with collaborative. Okay. Okay. Now I'm trying to share the screen, to share the file. Okay.
Thank you.
It doesn't say it's converting.
Yeah, it's just a few seconds that takes to do that.
Okay. Okay, I'm gonna try to open a different program to see if it works better. Okay. Instead of using the Acrobat, maybe
okay.
I can use the text SOP. Maybe it works better. Okay, so let's try to share now this and see if it works better. Okay, now it seems that it works. Share now. Okay, I'm sharing now with you. Can you see the the file?
Not yet.
Okay, it's loading most of them. Okay, it's loading most of them. But I can see select a slide to be shared.
Yeah, now it's
So
loading.
I have to go one by one here.
Yeah,
okay.
It's loading. Yeah. Now it's loading.
So,
yeah.
Okay, so if I
Now
go one by
you
one,
have to move with the pile underneath.
Okay, so I can work if so now you see
Yeah,
the one that
yeah. You see it's moving.
Okay.
Yeah.
Okay, so you see what I'm seeing. Okay.
I'm in Bayesian statistics now. Yeah.
Okay, so I was basically here. Okay, I was a little bit advanced.
We saw now the problem and dataset slide.
Okay, now it seems that it works. Okay, so let's continue. I'm sorry about that. I don't know what is going on. So the problem is that I have several algorithms and I have several instances, and now I apply the algorithm to the instances. I got some results, and then I can rank the algorithms for each of the instances. I can run the algorithm for each of the instances, and at the end, what I have as a result of the experiment is a set of permutation or rankings of the algorithms. Okay, so I have a permutation or rankings of the algorithms, and this is the data set that I want to work with. Okay, so what I'm going to do is to approach the problem from a Bayesian point of view. Okay, and this will allow me to obtain a more relevant information. Okay, it will give me more information than just a null hypothesis statistical testing. Okay, but our assumption is that the rankings has been produced by a probability distribution over the space of permutations. Okay, so I assume that they have been produced by a probability distribution. Of course, because we are in a Bayesian framework, we assume that we have an a priori distribution over the parameters of this probability distribution over permutation. So given the rankings, what we will do is to compute the a posteriori distribution over the parameters. Okay, this framework allow us to carry out some inferences. Okay, and this is the kind of inferences we would like to do. What is the probability that algorithm AI is the first in the ranking? Okay, so we can compute what is this using the Bayesian framework. We can compute this probability, and in addition, we can know what is the variance of this probability. Okay, we can compute what is the probability that algorithm AI is higher or lower than algorithm AI in the ranking, or what is the probability that algorithm AI is in the top K ranking of the algorithms. Of course, we can think we can think in more addition and posterior summaries, like the probability that a given algorithm is ranking a given position other than the first one, etc., etc. I'm not going to enter because I think we are with so many interactions, we are going to be a little bit out of time. So I wrote here population because it's really important to consider the population to take into account which is the population we are working on. At the end, we are trying to make inference about a population using a sample. So it's very important to have it clear what is our population. Okay. So with all this, in order to carry out the statistical, the Bayesian approach, what we need to do is to codify a probability distribution over the space of permutation. And this is not trivial, okay? This is not trivial. So let's go. How to codify probability distribution over the space of permutations. Okay, So if you think, I don't know if you have ever thought about how to codify a probability distribution over the space of permutations. So if you try to codify, let's say, in a brute way, you have to compute the probability of 1, 2, 3, 4, 5, the probability 2, 1, 3, 4, 5, and so on. So at the end, you would need, in this case, 5 factorial minus 1 parameter. So in general, you would need n factorial minus 1 parameter. So this is impossible. I mean, we cannot do this way. So we need to find other ways. We need to find other ways to compute or to codify a probability distribution over permutations. So if you're in the field of artificial intelligence, probably what it came to your mind is, okay, let's try to use probabilistic graphical models, because probabilistic graphical models has been used for codifying probability distributions in the field of artificial intelligence. Well, if you try to use probabilistic graphical model, you would discover that it's impossible, no way. You reach to the same situation of needing n factorial minus 1 parameters. So we need different ways to codify probability distribution over permutations, and particularly when you check in the literature, you discover that there have been many ways to codify probability distribution over permutations. One of these ways is to induce probability distribution using pair comparisons. So basically, what you have is a probability that item I is preferred to item J. Okay, item I is preferred to item J. You can think in basketball team, so you can think in products, or you can think in different things. And this is the general way of codifying probability distribution between using pair comparisons. And a particular example is the Bradley-Terry model, in which you have n parameters and the comparison are carried out in this way. So this would be one of our models. Okay.
Antonio, there is a question in the chat. Is it assumed that the algorithms are compared on a single objective?
Yeah, definitely. We are comparing them in a single objective. In order to compare them from a multi-objective point of view, what we usually do is to have. I mean, you can use different measures at the same time, but many of the times you compress all the measures in one. But anyway, this is one of the things that we are considering as future work, to consider several objectives at the same time. Okay. Okay, so this is one of the models. Another classical model is the Placket-Luce model. In the Placket-Luce model, we are given a set of parameters that they sum to 1, and then there is a definition procedure, and WI is the probability of choosing object I, and we have a sample procedure in which an object is choosing using theta. Okay, and then once one object has been chosen randomly, then we update theta by deleting this object, and then choose another object, and so on. And in this way, we get a ranking. Okay, the probability of any ranking is given by this formula, and the good point is that if we want to carry out inference, the probability of sigma 1 equal I is equal to WI. Okay, so computing the probability of an algorithm to be in the first position, it's trivial. Okay, it's trivial in the example. Finally, we have the Malus model or distance-based ranking models. Distance-based ranking models are a kind of exponential model that they are defined by two parameters, the spread parameter theta and the central permutation sigma 0. We need a distance between permutations, and this model is in some sense is similar to the Gaussian distribution but for permutations. Okay, so here you have the probability of different values depending on the distance to the central permutation. So when theta goes to 0, we have a uniform distribution. When theta makes bigger, the distribution is concentrated in the central permutation. Okay, so different distances can be used with the malus model, but the most common distance is the Kendall-Tau distance that measures the number of disagreements the number of disagreements between two permutations. So basically, what we have is that for each pair, it checks when the pair of indexes are in the same order in one of the permutation or not. In this case, we have P1 is 2, P2 is 3, sigma 1 is 1, sigma 2 is 3, because they are in the same order. So we count 0 in this case, but however, if we take the power 1, 3, we have that they are in a different order, so we count 1 and so on. Okay, so with this we have, sorry about this, it's a big word. So finally we compute the Kendall-Tau metric between these two permutations, that is 5. Okay, so we are gonna use these three probability models to carry out inference, and for each of them we are gonna consider different prior distribution. In the case of the Bradley-Terry model, we would use a Dirichlet distribution, okay, because these sum to 1, and a Dirichlet distribution sample points that they sum to 1. In the Plackett-Luce, given the literature, we saw that some authors use a gamma distribution for each parameter individually, and at the same time we would use a Dirichlet distribution. And finally, for the malus model, we would use a uniform distribution for the central permutation, and we will use a truncated exponential for the parameter theta. Okay, so we all have with all this we have the machinery, okay, and we can carry out some experiments to see what we obtain. Okay, so let's see some experiments. So I'm only gonna show experiments in artificial experiments, okay? So we are gonna simulate the result of an algorithm as a sample of a Gaussian distribution. So algorithm AI would be the result of algorithm AI would be simulated with a Gaussian distribution with mu I and sigma I. So a permutation is generated each time we sample all the algorithms, in fact, all the Gaussian distributions. And here you can see some of the parameters where we have used. We use 4 algorithms with different means. Clearly, 2 is, the first algorithm is the best, second, third, and 4. And we use a standard deviation equal to 1. Okay, the population in our case is going to be 10,000 permutations, and we consider a sample of 1,000 instance for the 10,000 permutations. Okay, so in order to compute our statistics, for instance, the probability of an algorithm being in the first position, the ideal situation is that we have a closed formula for this. Okay, that is the probability of sigma 1 equal I given the data set, and usually it's computed this way. But unfortunately, we have no closed form for the distribution we have considered. So we need to compute. In practice, we have to use Markov chain Monte Carlo to sample some values of the parameters, and then using these 1,000 values of the parameters, we compute what we want to calculate. Okay, so for each algorithm AI and probability, we compute the probability of the algorithm I to be in the first position for each value of the parameter sample. Okay, and we compute the mean and the variance of these 500 values. Okay, and you can see here the results. So this line, this points line is the real value, the one computed from the population, okay? This line is the one computed from the population, and this is the result of the Bradley-Terry model, the Plackett-Luce model with Dirichlet prior, the Plackett-Luce model with gamma prior, and the Malus model. As you can see, the result of the inference is really close to the value of the population, okay? Maybe you can find here more differences, but if you realize these numbers are not in the same scale, so these numbers are really, really small. So even when you can see some differences, there are not that much difference between them, okay? So the only algorithm that behaves, the only model that behaves in a different way is the Malus model that, as you can see, it didn't obtain the required value. Okay, here it did, but on the rest of the situation it didn't. Okay, what we also did was to compute the probability of algorithm I performing better than algorithm AJ. Okay, and in this case, what you can see is for each of the 500 values we obtain, we put a point randomly in this arc between A1 and A2. We put in this arc, okay, and taking into account the probability. So as you can see, the probability of A1 being better than A2 is 0.8. Is close to 0.8, but of course it's much higher between A3 and A4. Okay, in the case of A4, clearly the probability of A4 being better than the other algorithm is really low. Okay, so finally, I'm gonna show you examples of probability of an algorithm being in the top K ranking. Okay, so here you can see top 2 for the Bradley-Terry and from different models. So it's clear that that the results that we are seeing are those expected. I mean, except for the Malus model that it didn't behave as expected. Okay, so I had more experiments about the influence of the assumptions, but I think we are run out of time, so I'm gonna go straight on to the conclusions, if you don't mind. Okay. So the main, I think the main message to take home is that scientific conclusion cannot be based only on null hypothesis statistical testing. We need to go beyond that in terms of the analysis we can do and in terms of the knowledge we need to carry out scientific conclusions. Okay, I'm not saying that we shouldn't carry out null hypothesis statistical testing. What I say is that we should add as much information as possible in order to obtain scientific conclusions, okay, beyond null hypothesis. And we need to provide the community richer and more informative statistical tools. And this is one of the things we have tried to do. Another conclusion is that we should avoid yes or no statements. Okay, there is usually no yes or no statements. At the end, what we get with our method, it's a probability and a variance. I mean, we know the uncertainty of that estimation. That is also important. Well, the Bayesian framework accounts for many of the previous desirable properties. And of course, there are many issues that are related with the Bayesian framework. One is the Bayesian model selection, etc. That you can put in question our method. I didn't say anything, but all the information is all the code is available. So if you can use the code is available. The paper has been recently accepted in IEEE Transaction on Evolutionary Computation, And all the experiments are reproducible, of course, and all the code is available, so you can freely use this code in order to carry out your own analysis. Okay, and that's all. And I'm sorry about the technical issues. I'm sorry.
Thank you very much for your very nice presentation. And I open the floor for 1 or 2 questions. So, José, could you give the right to microphone and the camera? Because there is a question in the chat.
Yeah, I think I can see the question in the chat.
Okay.
Could you possibly, okay, how restrictive is the assumption about the use samples coming from a normal distribution? Is it possible to further robustify the results? Well, in fact, I only showed you samples from a Gaussian distribution in this example, but in the paper, you can find results with real data, okay? That probably they don't follow a Gaussian distribution. Furthermore, I had no time, but I couldn't show you experiments when there is no. Another problem is the unimodality of the models, and we show experiments where the data sets are not unimodal. Okay, and how the algorithms behave in that scenario, and the behavior is relatively good. Okay. So thanks for the talk. Could you possibly direct that to some literature on this topic, please? I can give you, if you wait for a while, I think I can give you the reference of the paper. Okay, it was published. I mean, it was accepted two weeks ago, something like that. So let me wait a minute. I can give you the reference to the paper, okay? No, is this what I need? Momentum. I should be, okay. Wait a minute. The title of the paper is this one. And this is the title of the original paper. And if you check in the IEEE transaction on evolutionary, you will find it. Okay. Also, I think we have it in archive, so you can check in archive for it. So I don't know if there are more questions.
I cannot see more questions, so we would like to thank you very much for such an interesting presentation. And for the rest of the audience, we will see you back if you have the time next Monday. Thank you so much to everybody.